In this problem, assuming there's nothing to hold the car to the track, we have to find the maximum speed at which the roller coaster should travel at point B. So as we always do, we are going to visualize the problem. We're going to start by defining coordinates, and then we're going to draw a free body diagram for the object of interest. In this case, we're going to draw a free body diagram for the car. Very important to identify the coordinates. So for circular motion problems, we have the tangential direction. So it is to the right because at point B, the car is moving clockwise, and then the radial direction is directly downwards towards the center of the circle, and there's only one force acting on the object, and that would be weight. Normal force is 0 at this point because it says in the question, it states that there's nothing to hold the car to the track. Normal force is the force exerted by the surface on the object, right? If there's nothing to hold the car to the track, the normal force would become a 0. And if the normal force is 0, you will see maximum speed for the roller coaster. And weight is equal to mg. The radius is equal to 15 meters. You can see it in the circle. It's 15 meters. And applicable concepts. So this is chapter 6, circular motion. And have we specified the coordinates? Yes, we have specified the coordinates. Tangential direction, it is tangent to the circle at point B, and then radial direction towards the center of the circle. And the symbols of what we are trying to find, we're trying to calculate the speed of the car at point B. We are actually trying to calculate the maximum speed. And the unit is meters per second. Speed is a scalar quantity. And let's plan the solution. So we are going to use Newton's second law. Net force acting on the car is equal to its mass times acceleration. I'm going to use the component form of the Newton's second law. So the net force acting on the car in radial direction is equal to mass times centripetal acceleration. And then the centripetal acceleration is equal to tangential speed squared divided by the radius. And now let's execute the plan. We're going to use Newton's second law, the component force. If you look at the free body diagram, there's only one force acting on the object. That would be weight. And it's acting towards the center. So it's acting according to our coordinate system. It's going to be positive. Mg is equal to mv squared over r, and we can cancel out mass because it's common for both sides of the equation. And if you separate v squared on one side, you get v squared is equal to gr, and you take the square root of that. G is 9.8 meters per second squared times radius 15 meters. And you can see you have meter squared divided by second squared inside the square root, and when you take the square root of that, you get meters per second for the unit of speed as we expected, and 12.1 meters per second. So if the car goes faster than this at point B, it will definitely fly off track, or else you need a higher downward normal force to make sure that the car is not going to fly off the track. So we have solved for the speed of the car, and the problem is complete.